Well, we're beginning in our last full unit here. And full unit, this is our last full unit that we're covering with a full exam and everything, is oxidation and reduction equations. And really, oxidation and reduction equations we've looked at before. We've seen a ton of oxidation reduction reactions, but we've never described them as oxidation reduction reactions. What oxidation reduction reactions really are, and this is how I like to think of it, is a transfer, reactions that have transfer of charge. Not even of charge, I don't like that word. Let's say transfer of electrons. So there is an electron flow within the reaction. And just like any other chemical reaction, remember, chemical reactions, they have to be balanced based on mass, based on number of atoms, right? Well, we also have to be balanced here based on the number of electrons. So when we're looking at oxidation reduction reactions, what we're looking at is we're really looking at that transfer of electrons, and we want to see where they come from and where they go in any chemical reaction. So to look, at a chemical reaction we do quite often, one that we've used recently, we have magnesium, right? And magnesium reacts with, well, say hydrochloric acid, and we all know what this produces. It produces some gas, hydrogen gas, H2, and a magnesium chloride. So what we want to do when we look at a reaction like this, and previously we would have just described it as a metal acid reaction or as a single replacement reaction, but now we want to describe it as an oxidation reduction reaction and see what's happening. Well, here's some things we should already kind of know from doing formulas, is that when hydrogen is bonded to something, hydrogen has a +1 charge. Okay, so we know that, and we know that chlorine, when it's as a chloride, it actually has a -1. So these things within the compound, these are their oxidation numbers. They're really, we should get away from saying they're charges because they're not fully charged. They're in a bond, and this is kind of a covalent bond, so they don't really have true charges, but we'll call them their oxidation numbers. So hydrogen has a +1 oxidation number in this compound. Chlorine has a -1. If we go over to the other side of the reaction, I'm leaving some things blank here temporarily, and look at magnesium. Well, we know magnesium is an alkali earth metal. It's in the second row. Notice it's bonded to 2 chlorides. Chloride, again, is always -1. Well, if chloride is -1 and there's 2 of them, that gives us an overall -2, so magnesium has to be +2, which is what we'd expect from the periodic table. Again, it's an alkali earth metals in the second row, so we would expect that it would have a +2 oxidation state. Okay, those things we already know. Let's go back and look at the unbonded compounds. If magnesium is by itself, it is assumed to have a 0 oxidation value. It doesn't have a charge. There's no partial transfer of electrons when magnesium is all by itself. Same thing when hydrogen bonds to itself. It has an oxidation number of 0. It is no transfer, no displacement of charge by any way. Now, let's see what's happened in this chemical reaction. Notice we had magnesium going from a 0 to a +2 state. So magnesium changed its charge. It went from a 0, it went over to a +2. So it got more positive. If a compound gets more positive, we're going to call that oxidation. And what that means is it lost electrons. And if we look, how many electrons did that magnesium lose? Well, the magnesium lost 2 electrons. And I'm going to put lost 2 electrons right there. So magnesium lost 2 electrons in this process. Now, what else changed? Now, so here's the thing. If we're looking at oxidation reduction problems, there's a reason they're called oxidation. Well, I should put and reduction, is because there has to be a reduction part going on too. So magnesium can't just lose 2 electrons. Those 2 electrons have to go to somewhere. Well, where did they go? Well, notice the other thing that changes charge. We have a hydrogen going from a +1 to a 0. So what happened to hydrogen is hydrogen actually, it got more negative, right? It actually got more negative. It gained electrons, right? So it gained electrons, got more negative. And so we would say it was reduced in this chemical equation. So hydrogen was reduced. And how much was it reduced? Well, notice it went from a +1 to 0, but there's 2 hydrogens here. So if this equation was balanced, there would be a 2 in front, and that's where our 2 electrons went. So each one gained 1 for a total of 2 electrons. Okay, so pretty easy. That is, essentially, that is what we are doing in oxidation reduction reactions. We are figuring out our oxidation numbers, we're going to identify what has been oxidized and what's been reduced. However, as you may have guessed, this is a pretty easy example. So let's go back and let's look at rules for how we assign these oxidation numbers, because again, this is something we talked about when we were doing naming. We needed to know, but we didn't look at it in too much terrible detail. So the most important rule, and there's probably too many rules on this list. We could probably sum it down a bit more easily than this. But anyway, rule number 1 is still important. Any uncombined element, any pure element, the oxidation number is always 0. So sodium as a metal is 0, just like in our previous example. Magnesium was 0. Hydrogen gas is bonded to itself, but its oxidation state is 0. That's the first thing we're going to look at. The oxidation state of a monatomic ion equals the charge on the ion. So what that's saying is if we see chloride by itself bond to something, or say oxide O-2, or bromide, that the charge that we'd expect is going to be the oxidation number. And here's one thing that I would actually prefer that you do. When we look at that, I would actually recommend that, yeah, we can look at our halides. Our halides are pretty predictable, but we should also skip down. We should look at this rule right here, that oxidation of oxygen is almost always -2. And that's one that we use a lot because oxygen is in a lot of compounds. There's a couple other important rules that are on here. So oxygen is always -2. Halides are always -1. Again, they broke these apart, so there's probably too many rules than we need. This one, oxidation of hydrogen in most compounds, is a +1. Again, and they always throw in these exceptions, and we'll see those exceptions, but we don't need to focus on them at this point. So I'm going to take those rules that on that list, and I'm going to break them down into really 4. Number 1, we look at pure elements. So let's just say this. Let's make that list of rules much easier. Pure elements, the oxidation state is 0. Next thing I'm going to look at is oxygen is -2. Unless it's a peroxide, so there is an exception. If it's like H2O2, then oxygen is a -1. That's pretty rare. Oxygen is almost always -2. Next thing I'll look at is hydrogen. Hydrogen is +1. And again, there's exceptions. If it's bonded to an alkali metal and another metal that's typically +1, then it might be -1. But again, that is fairly rare. We're not going to see it. So that's how I'd go down the list. I'd say, okay, let's look at pure elements. Let's look at oxygen. Is there any oxygen in our compounds? Let's look at hydrogen. And then we might look at alkali and alkali earth metals. And we know those charges based on their column, right? They're either +1 or they're +2. The other thing we would want to look at is, then maybe I'll look at halogens. And halogens, again, are very often, if they're by themselves, going to be -1. Those are, I said 4 rules. Okay, I gave you 5. Then we're going to figure everything else based off of those rules when we're looking at examples. So again, the first step to determining if something's being oxidized or reduced is we have to find the oxidation number. So we'll have to do quite a few of these. So say we have calcium carbonate as our compound. We want to figure out the oxidation states of all of these things. Again, I'm going back to the rules that I gave you. I'd start with the oxygen. Say oxygen is almost always -2. That's the oxidation state on oxygen. Now notice there's 3 of them, so that gives me an overall -6 charge. That's all my -6 charges. Now let's go to the other side of the compound. Calcium is an alkali earth metal. There's very rare instances where alkali earth metals are not going to be +2. So notice we have a +2. We have a -6. That means my carbon has to be +4. So my oxidation states, calcium is +2, carbon +4, oxygen is -2. Now that one was pretty easy. Let's maybe do something a little bit more difficult. Here's a compound we see a lot when we're talking about oxidation-reduction reactions, but again, we'll break it apart the same similar way. Oxygen is -2. There's 4 of them, so the overall negative charge in this compound is a -8. I'm going to go over to my other side, potassium. Potassium is in the first column on the periodic table, so it will be +1. That's going to leave the charge of my manganese at a +7, which is odd, but it's possible. So my oxidation states here are potassium, +1, manganese, +7, and oxygen, -2. That is the process we go through. If we see something like this, well, this is zinc. Zinc would have an oxidation state of 0, right? If we see something like this, Br2, again, that's still pure bromide, that would have an oxidation state of 0. So once we can determine oxidation states on individual compounds, maybe we look at one more here. What about, I don't know. I'm running out of creativity with my compounds. Magnesium bromide here. Well, in this case, we could look at magnesium. It's an alkali earth metal. It's probably going to be +2. Bromide is a halide is going to be -1. There's 2 of them, so that gives me the overall -2. So then my charges are still canceling, which again is what we need to have happen within our compounds. Now it's possible at some point that they might give you just the polyatomic ion, say nitrate, NO3, with an overall -1. Well, that's fine, and now we just want to add up the oxidation states on each of these elements to get that overall -1 charge. So again, oxygen is -2. There's 3 of them. That gives me an overall -6 charge. So whatever nitrogen is, it has to give me that overall -1 charge. So in this case, nitrogen would be a +5. So nitrogen is +5, and oxygen is a -2 in this compound. One more of those? Sure, let's do our phosphoric, or phosphate ion, or phosphite ion, actually, PO3 with a -3. Again, oxygen is -2. 2 times 3, that's an overall -6. So whatever phosphorus is in this compound, it has to yield that overall -3 charge. So phosphorus must be a +3 in this compound. So in phosphite, phosphorus is a +3, oxygen is a -2. Notice if we look at phosphate, PO4 with a -3 charge, again, oxygen is still -2. That's why we rely on oxygen so much when we look up the oxidation states. Gives me an overall -8. To get that overall -3, phosphorus in this compound has to be a +5. I'm sorry, I can't do my basic math. 5 and -8 gives me that overall -3. So phosphorus is a +5. Oxygen is a -2 for our oxidation states. And again, we're always interested in the oxidation state on the individual element, not, again, that overall charge. We need to know that so we can figure out the oxidation states. But when we're looking at the oxidation-reduction reaction, we're interested in the oxidation states of the individual elements. So again, a lot of the reactions we've looked at before, we haven't talked about them as oxidation-reduction reactions, but they really are. So notice this one from your book. This is just sodium and chlorine making sodium chloride. Very basic reaction that we've looked at. Actually, a rather dangerous reaction, but pretty basic. So we have sodium. Notice sodium, they figured out the oxidation states here. Sodium is by itself, so it has an oxidation state of 0. But here, when it's bonded to chloride, it's an alkali earth metal. There's a transfer of electrons going on, so its oxidation state is equal to its charge state. It is a +1. So we have a 0, and we have a +1. And so in that, remember, if it got more positive, then we can say that our sodium was oxidized. Oxidized when it gets more positive, and it lost an electron. Now, in the second part of this, we have to see where that electron went. And you can probably guess that, notice chlorine here is by itself, so it has an oxidation state of 0. Here it is bonded to the sodium, so it has a -1. So notice it got more negative, so it gained electrons. So my chlorine was, or is, reduced. So chlorine was reduced, and it gained the electrons. Notice we can see that in this example. So chlorine gained electrons. And notice, this is the one thing we just have to be careful of. Chlorine is diatomic, Cl2. So we had 2 chlorines. Each one gained 1 electron individually. As a total, they gained 2. That's in our balanced equation. You notice we have a 2 in front of that sodium. So really, when we balance these and put them together, that's where our 2 electrons come from. That's kind of what we get into in the next section, where we have to balance these half reactions. So we have to see what gained electrons, what lost electrons, and how that balances. So really quickly, some of your section review questions, and these you should go through yourselves as well. So notice bromine gained electrons. If it gains electrons, it's reduced. Notice sodium lost electrons, so it's oxidized. Lost electrons in this instance, it's oxidized. Gained electrons, they're on the left side of the equation, it's reduced, and so on. Okay, which of these represent oxidation-reduction reactions? Well, the only way we know if they're oxidation-reduction reactions is we have to go through and see what the oxidation states are on each of the compounds and see if they change. Notice in the first one, we have to figure out the oxidation states. Again, we'll start with oxygen's -2. If there's 3 of them, that's an overall -6 charge within the compound. Notice there's no overall charges, so the compound itself has to be neutral. Potassium, we could assume, is a +1. So the difference between the +1 and the -6 means nitrogen in this case, and I'll try to write in another color, is a +5. So that's what all our oxidation states were when we started. We had potassium +1, nitrogen +5, and oxygen with the -2. Okay, so you can see them. All right, on the other side of the equation, notice what we have. One thing sticks out to me right away is I have oxygen by itself where it's 0. So I know oxygen went from a -2 to a 0, so it actually got more positive. Oxygen, interesting, was oxidized. So oxygen was oxidized in this. If oxygen was oxidized, we have to find something had to be reduced. Notice oxygen is still in this compound as a -2, so not all the oxygen was oxidized, but some of it. There's only 2 of them in this structure, though, so that's our overall -4. Potassium, I'm going to assume is still +1, so it's nitrogen. The difference between +1 and a -4 is a +3. So my nitrogen went from a +5 to a +3. It actually got more negative. Its charge went down, so nitrogen was reduced. So this is an oxidation-reduction reaction. Look at all those scribbles. Isn't that fun? Sorry for all the scribbles. Let's try the next one. And you can probably just look at it maybe and see whether or not it's oxidation reduction. Notice if we have compounds by themselves and then in a compound, again, in a compound copper and then by itself, we know it's an oxidation reduction because things in compounds have to have oxidation states. Things by themselves have to be 0. So hydrogen here is 0. Within water, it's going to be a +1. Copper here bonded to oxygen, and we're going to assume oxygen is -2, so copper is a +2. Over here by itself is 0. So copper went from a +2 to a 0. It was reduced. It got more negative. It must have gained 2 electrons each element. Hydrogen went from a 0 to a +1, so it was oxidized. And it lost 1 electron each. And that's what we need to know. Now, I'd encourage you to look at these last 3 of these as well. Now, be careful because not every chemical reaction is an oxidation-reduction reaction. So do not try to make it so. If there's something that doesn't work as an oxidation-reduction, there's no changes in charge, it's not going to be an oxidation-reduction reaction. So with that in mind, maybe I'll do this last one. So here, sodium is a +1. Oxygen, even though it's hydroxide and it's in this position, it's still -2, or our oxygen. Hydrogen then has to be a +1, so all of our charges cancel. We have a neutral compound. Over here, hydrogen is +1. Chlorine is -1. Okay, so again, those are an overall neutral compound. Here's sodium bonded to chlorine. Chlorine by itself is the chloride ion. That's a -1. Sodium is a +1. Now notice, sodium was a +1 over here, so sodium didn't change. Notice chlorine was a -1 here, a -1 here, so chlorine didn't change. And now if we look at the water here, hydrogen is a +1. There's 2 of them for that overall +2 charge, so we have a neutral compound. Oxygen is -2. Notice over on the other side, oxygen was a -2, hydrogen was a +1. So C is not an oxidation-reduction reaction. There's no charge transfer in this reaction. So it is very possible that you are going to run into some that aren't oxidation-reduction reactions. Not everyone is. The only way we know is going through and identifying the oxidation numbers on each and seeing if they change. Thank you for coming along on this ride with me through oxidation numbers. I hope you enjoyed it, and I hope you enjoyed part 2, 19.2 on balancing oxidation reduction half reactions.